Okay, so now that we've introduced the idea of a force, we want to talk about more specific applications of forces. In this video, we're going to talk about forces and acceleration. All right, so this is in this video, we'll talk about forces, we'll talk about how they relate to acceleration, and we'll talk about Newton's 3 laws of motion. Okay, so as you might remember, the definition of acceleration is that it's a change in velocity. And of course, a velocity is a measure of how fast something's position is changing. In other words, something that has a velocity has motion, right? Now, if something is accelerating, the motion is changing. So when forces cause a change in motion, acceleration is always involved. All right? An example might be this golfer here. He has swung his club, the club head has contacted the ball, and the ball's motion has now changed. It's gone from rest to some velocity in a really short period of time. That's a very high acceleration at the point of impact with the ball right there. All right? Cool. That's just a visual example of acceleration caused by a force. All right. So this brings us to Newton's laws of motion. All right. In particular, the second law of motion. All right, which basically states that force and acceleration have a direct relationship with each other, and that relationship depends on the mass of the object that's being accelerated by the force. All right, so here we have an example of a relatively small airplane. A force is acting on the body of this airplane. The force is being supplied, actually there are several forces, but the one we're concerned with is the force that is being supplied by the propeller. Right there. All right, so this engine is relatively small, as engines go on airplanes, because the plane has a relatively small mass. All right. Now take a contrast to that. Here we have a Boeing 747 by Korean Air. This has a very large mass. All right, as you're quite familiar with if you've ever ridden on one of these sorts of airplanes. All right, the mass of this airplane is quite large. It needs a lot more than a little propeller in order to get it going. So much larger mass means much larger force in order to get the same kind of acceleration. Okay, so here we've got 1, 2, 3, and 4 jet engines is what this airplane needs in order to get it accelerated fast enough to fly. All right, so what's the bottom line? The bottom line is that force is proportional to both mass and acceleration, right? So if we want a higher acceleration with the same mass, then we're going to need a larger force being applied. If we want the same acceleration with a larger mass, then we also need a larger force, all right? If we decrease the force applied to a given mass, then the acceleration will decrease, and so on. So you can see how that's related. That's a very simple 3-variable equation, which you know from algebra. You can manipulate this in various ways, and if you change certain quantities, then other quantities are going to change. Cool. Now, specifically, if we want to talk about a particular application of Newton's second law of motion, or Newton's second law, we can look at it this way. A specific example of that previous equation, F equals ma. Let me just rewrite that up here. F equals mass times acceleration. Right, so we're talking now about a specific application of that formula, which is weight. All right, weight is a force, and it's measured in newtons. All right, you might be familiar with talking about person's weight as being in kilograms, but that is not accurate in physics terms. Weight is not a mass. Weight is a force. Kilograms are a measure of mass. All right, weight is measured in newtons. I'm sure this is not going to change the way that you talk about your weight to your friends, but hopefully this will change the way that you talk about and think about weight and mass in terms of physics class. All right. So here's an example of just a guy standing here, right? And this is the altered version of the equation. Weight is equal to mass times g. Now you might remember that g, little g, is the acceleration due to gravity. So g is an acceleration, w is a force. So really we just have the equation F equals ma. It's just a particular version of the equation, right? You've got a force in weight, you've got the mass, and then you've got an acceleration, which is g. So this is really just a special form of that equation, F equals ma, that we use for solving for weight. All right, so here's an example. Let's suppose this guy here has a mass of 75 kilograms. Then the question is, what is his weight? And we can solve that rather quickly right up here in this blank space. All right, weight is equal to 75 kilograms times g, which is 10. So the weight there is going to be 750, and the units of force is newtons. So 750 newtons is this guy's weight if he has a mass of 75 kilograms. All right. We're trucking along. We're covering lots of territory. And that brings us to Newton's first law. Right? We went a little out of order, but that's okay. So Newton's first law, an object's motion will not change unless a force acts on the object. All right, so this means that if an object is in motion, it's going to stay in motion unless some force acts on that object. If an object is at rest, it will stay at rest unless a force acts on it. So here's an object that's in motion, right there, the tennis ball. It's in motion this direction, right, going that way towards this tennis player. She is going to use her racket in order to supply a force. That force is going to be in that direction, opposite to the motion of the ball, right? So what's going to happen? The ball is going to smush against the racket in a split second, and then its motion is going to change, right? Previously, the ball was going this direction. After it hits the racket, the ball will be going that direction, back toward the opponent, and hopefully in a place where the opponent can't reach it, right? That's the whole goal of tennis. So that's an example of using a racket, the force of the racket, to change the motion of that tennis ball. All right, another example. There is an object that is clearly at rest, right? That lion is at rest. It is not going to move unless some force acts upon it. All right, now maybe it'll wake up and the force will be the force of its own muscles. Possibly one of the trainers is going to get annoyed with the lion and maybe poke at it with a stick or something to try to get it moving. That might not be a very good idea. It is a lion after all, but, you know, maybe. I don't know. Maybe a trainer would want to do that. I'm not sure why the trainer would want to do that, but in any case, that lion is not going anywhere unless some force acts on it. Okay? And then this brings us to the third law of motion, which is something that you've probably heard before. Every action causes an equal and opposite reaction. Or maybe for every action, there is an equal and opposite reaction. Okay? So an example would be this rocket. The action of the rocket occurs inside the rocket's body here. There is a chemical reaction. The result is that gases are released out the back here. They're hot, explosive gases. They're released through nozzles going that direction. So the force is the gas, right? The gas is being released from the body of that rocket. All right, so the force on the gas is in this direction, downwards. The reaction, then, is on the body of the rocket, and the body of the rocket will respond by going the opposite direction that way. All right, so the force on the gases is downwards and back, and the force on the body of the rocket is upwards and forward. Okay, so action, reaction. Another example, hopefully none of you have ever seen this firsthand. You've got an action and a reaction, all right? So the action might be that this car was driving that way, and then the reaction, and the action then is that this car hits that car. Gray car hits blue car, right? And causes blue car to crumple. But there's a reaction, unfortunately, for the driver of the gray car, right? The reaction is that the blue car acts with a force on the gray car, and that causes it to crumple. So what we have here is action and reaction. We have change in shape, we have change in motion. Forces can be rather dramatic and destructive sometimes. So the force of the gray car acting on the blue car causes it to crumple. The force of the blue car acting on the gray car causes it to crumple. All right, so forces have causes. Action, every action has an equal and opposite reaction. Okay? Another example might be if you punch someone in the face, which I hope you never do. But let's suppose you do. Your hand causes a force on that person's face, which if you punch hard might cause damage. The interesting thing is that their face is going to cause a force on your hand. That's the reaction, all right? And if you're not careful, you're going to hurt your hand by punching them in the face. So that's if you ever need another reason not to punch someone in the face, there's one for you, all right? Punching someone in the face could very well hurt your own hand, all right? So anyway, there's some examples of forces and acceleration and reactions and so on. Newton's 3 laws of motion, all right? Law number 1 is that a body in motion will tend to stay in motion unless a force acts on it. Body at rest tends to stay at rest unless a force acts on it. Law number 2 can be summarized by the equation F, force equals mass times acceleration, F equals ma. And then law number 3, every action will cause an equal and opposite reaction. All right?